I took part in the Jaca crystallography school in Spain recently. It's a fantastic school, and they also had some really nice example structures, and I promised to make some videos out of those. So this is the first. This is how OLX2 opens for you. This is July 2023. It's the version 1.5 release version. And in Start, you find those three dots. You click on them, and the first structure at the moment here is Jaca A02. And you download it by clicking on there. So that sets everything up. It gets the structure, and there's no structure, right? There is no atoms yet. It's not solved. That's our job. We can have a quick peek at the data quality. It's very good data here. There's no problem to be expected. We also know it's dark green. Dark green usually means something is not bad. And anyway, we head over to work, and over here in structure solution, we are just gonna select OLX2 solve and solve the structure. So this gives us electron density maxima in that structure. We can click on this orange button here, so that puts things as closely together as possible. And we can see there are 2 or 3 stronger peaks and the rest is quite weak. The strongest one is this. The formula tells us there's rhenium, so that's got to be that. This one here is bromine. How do we carry on now? So Control Q, or pressing this button, so this will toggle the Q peaks, the density peaks, with bonds, hiding them all together and showing them. So there's nothing very clear here. So for those structures, it's sometimes best to just leave it with the 2 atoms that we know and then refine it. So I'm clicking on the refinement settings. We're going to use OLX2 refine throughout the series, and I'm hitting refine. So refine will refine that structure, and hopefully this will sharpen up some of the other things. And we can already see Control Q, so now that looks a little more like something that could be a structure. So these things look like CO2. This one is probably not real, so I'm going to delete that. That one doesn't look real. And I can try to put it all together, and they have been all put together, and now that one doesn't look like it's real, and that one doesn't look like it's real, but that looks like a molecule. There's one on here, so just selecting it and delete on the keyboard. So what I'm going to do, everything that's here, I'm going to just call a carbon. It's a shortcut, and I'm going to refine that. Because I'd like to demonstrate a couple of things. So first of all, there were some that I didn't delete, so those big guys, delete them. And now we don't need the Q peaks anymore, but what we can see, some of those spheres are smaller than others. So that means more electrons are concentrated in there, so we need to select them. And presumably that's CO. It could be CO or C, but it's CO because the oxygen is the outer one, that's the smaller one. Selecting that, making them oxygen. And let's refine that. And I deliberately leave these ones a little bit too small, so these are clearly nitrogens. But the first thing I'm going to do, I'm going to make something anisotropic, just those 2. The R factor is displayed here. And just making those metals anisotropic will reduce the R factor quite significantly and sharpen everything else up. So Control M, or clicking on this show map, really should show us, well, there is some density around the metal. That's normal. That's what you can expect around a heavy element like this, especially when the absorption coefficient is large, as it is in this case, and maybe the crystal wasn't ideal, or maybe it was too big, or the absorption correction hasn't been done properly. We don't know. We have no information about this structure. We don't even know how big the crystal was. Right, so this tells us some green around here, so that is that these are nitrogen. So this is the same information. The balls are a bit too small, and there's this green, the unassigned density around it. And we're just making them nitrogen, and let's make them anisotropic in the same go. We just click on that, makes everything anisotropic. And we can also tell those colors are all green because the formula that we've been given actually turns out to be correct, but hydrogen atoms are missing. We click on add H, that adds the hydrogens, and that should be the model more or less complete. Control M is telling us there's nothing happening, nothing missing out there somewhere. What we need to do now is assign the weight, update the weighting scheme. So this will deal with this red goodness of fit field here. So this, after a few cycles, both of those values should become green, and this should become green, and it does. And we do this again. Now, at the moment, we have hopefully a settled structure. Yeah, the structure is settled. We can also make more cycles happen here. So we can, say 11 cycles. OLX2 refine will actually stop when it's settled. So it was already settled. I just did one cycle and that was it. Now we don't have a CIF file, a crystallographic information file. You click on ACTA, and that way OLX2 also produces the CIF file, which is ready to be sent. It's a complete CIF file that you can use. Now in this particular case, we have this add-on, the CIF Plus module, and that gives you a view into the CIF file if you click on it. And this will show us there's a lot missing information, and that's because, as I mentioned, we only had the HKL and INS, and that's not really very good. We really need to know about what software was used for the data collection, what diffractometer was used, how was the cell determined, what was the crystal size and color and shape, and so on. So there's a lot of information that's missing here, but normally you wouldn't be in that situation. Also, mu, the absorption coefficient, is quite large. So that's probably why. Yeah, this isn't extremely narrow, so this is a bit wider than it maybe should be. That could be absorption. Anyway, we have the structure solved and assigned, and we got something that's fairly decent. Now, just to clarify here, so I used OLX to solve. If we use shell XT, which is another option that we can use for structure solution program, we just click on solve, as is the only pop-up box in OLX2. Are you sure you want to solve it again? Yes. So this shortcuts a lot of the work we've done. It actually does the atom type assignment by itself. We then just need to go to toolbox work and make it anisotropic and add the hydrogen atoms to it. Once the hydrogen atoms are added, go back and adjust the weighting scheme. And do this a couple of times, so we are very, very quickly where we were before, except of course structure solution did all the heavy lifting here, so we switched the actor on again, a final refinement cycle, and this is the structure solved in a couple of minutes. Thanks for using OLX2.